Hello and welcome to Physics Teacher. This video is going to be a tutorial for my grade 12 chemistry class, all on our unit on thermodynamics. Let me give you a quick preview of all the questions we're going to go over. I'm just going to double check some definitions with everybody. And then we're going to do a question on physical changes, and then chemical changes and the heat involved. And then we're going to do a question on Hess's Law and enthalpies of formation. And then we're going to look at nuclear equations. And finally, E equals mc squared. So those are the questions we're going to do. If you only are interested in one or two, you can skip to them in the video. Otherwise, let's get started. All right, so first I think it's important, because in English we use so many of these terms interchangeably, to understand the definitions in chemistry. So temperature is the average kinetic energy of all the particles that are bouncing around in some substance. Thermal energy is the sum of all kinetic and potential energies that exist. Heat is the transfer of thermal energy from one substance to another. And enthalpy, which we use a lot in chemical changes, is a measure of that stored potential energy, sometimes called heat content. So this is an example of the principle of heat exchange, which we say that Q gained is going to equal the negative Q lost. So the amount of heat gained by this first sample of water, whose temperature is going to increase when these two are mixed, is going to equal the negative of the Q lost by this sample of water that is going to lose that thermal energy. Okay, now since this is a physical change, and we have no change of states either, so Q gained is going to equal mc delta T for the first sample. So I'll just call this 1, and I'll just write 1 and 1. And that's going to equal negative the Q lost. I'll call this the second sample. So we have M2 C and delta T2. And the reason I didn't write C1 and C2 is because in this question, both samples are water. It is possible there'd be something else, but in this example, both samples are water, the C's are the same, and because the C's are the same, we could actually cancel them on both sides of the equation. So now what we're left with is the first mass, which is 225 grams. So we've got 225 grams. Multiplied that by the change in temperature. Change is always final minus initial. So the final we don't know. And the initial for this sample was 12 degrees. And that's going to equal the negative of this mass, 475 grams. Again, we don't know the final temperature, but the initial temperature of our second sample is 96 degrees. And now we just have to rearrange and solve this equation. So to do that, we need to collect our final temperature terms. Now we have one here and one here. So we're going to have to expand these brackets first. So we're going to have 225 grams. If we multiply this in, like so, we're going to have that times TF, and then we'll have minus 225 grams, because we have a negative there, times that 12 degrees Celsius. Do the same thing on the other side of the equation, so minus 475 grams times by the final temperature, and now we have a double negative, so plus 475 grams multiplied by this 96 degrees Celsius. All right, so collect like terms. I'm going to bring this term to the other side of the equation by adding it to both sides, and this term to the other side of the equation. So this is going to give us, on one side, we have 225 grams times that final temperature. And this is going to become positive, so plus that 475 grams times the final temperature. And that's going to equal to, we have this 475 grams times 96 degrees Celsius, and then plus this 225 grams times that 12 degrees Celsius. So now you can see that we have final temperature all on the left side of our equation, and we have one variable for each term. So we can factor that out. So pull out a TF, and that leaves us with 225 grams plus 475 grams, all equal to everything we have here on the right side of the equation. So when we add these two together, we get TF times a total of 700 grams. And that's going to be equal to, let me put all this into our calculator here, we get 48,300 grams degrees Celsius. So now we divide both sides by that 700 grams, and we'll be left with our final temperature. And so that equals our final temperature, which is, put this into our calculator, so 48,300 divided by 700, and we get 69 degrees Celsius. All right, our next question is going to be looking at chemical changes. So here we have butane, and it's in an exothermic combustion reaction. Now here, in this one, we have 2 moles of butane. So what I want to do is I want to figure out first how much energy is released for just 1 mole of butane. So I'm going to rewrite this equation, but divide all of our coefficients by 2. So this is just going to give us 1 mole of butane. And then, yeah, we have a fractional coefficient there. Don't worry too much about that. And 4 CO2 plus 5 H2O. And then we have to divide that energy by 2 as well, which gives us 2,871 kilojoules. So I know that molar heat of combustion is going to be negative 2,871 kilojoules. Now we write this as negative because it is in our product term. It's exothermic, so negative just means exothermic. Now we want to know how many grams of this butane is required to heat up this much water from 15 to 48 degrees. 15.5 to 48.5 degrees. So first let's figure out how much heat is required. So this is like our previous question. We're going to do Q equals MC delta T. So we have 7.25 kilograms of water times that by C. So C is 4.18 joules per gram degrees Celsius. And then we have our change in temperature, which is final minus initial. So final is 48.5 and initial is 15.5. So right away you might have noticed that typically what we use in chemistry is this value for C, which is in grams, but our mass is in kilograms. So you have to do something about that. If you like, you can simply rewrite this as 7,250 grams. And when you do that, we are going to get around 1 million joules. So 1 times 10 to the power of 6 joules. And if you like, you can divide that by 1,000. So we get about 1,000 kilojoules. So now the question is, that's how much heat is actually given to water to heat it up from a reaction of n number of moles of butane multiplied by the change in enthalpy for combustion of butane. So if we want to figure out the number of moles, we're just going to take Q, which was about 1,000 kilojoules, and divide it by essentially our enthalpy change for combustion, which is, should write for every 1 mole. And I'm going to leave out the negative because we don't want to have negative moles in our answer. That doesn't make sense. So 871 kilojoules per mole. So that will give us about 0.348 moles. Well, once you have that, you can go ahead and say, well, number of moles is going to equal to mass divided by molar mass. So rearranging, we get mass equals number of moles times the molar mass. Now we know how many moles were required. It's 0.348. And you can look at your periodic table, figure out what the molar mass is for 4 carbons and 10 hydrogens, which gives you about 58 grams per mole. And we end up with about 20.1 grams. There's our answer. All right, so our next question is a Hess's Law question. So we need to find the change in enthalpy for this reaction, given what it is for these two reactions. So first thing I like to do is I do like to sort of take these out of the equation. So I'm going to write that for this one, delta H is negative 221.0 kilojoules. And for this one, I'm going to write that delta H is negative 483.6 kilojoules. All right, so now let's look at just these two equations, and we need to try to get to match this one here. So our first one has 2 carbons as one of the possible reactants. In the equation we want, we only have 1 carbon. So what I'm going to do is I'm going to take this equation I, and essentially I'm going to divide it by 2. So what do we get when we do that? So we're going to get 1 carbon. We're going to get half an oxygen, and that is going to give us 1 carbon monoxide. Now what we also have to do is take that delta H and divide it by 2 as well. So when we do that, we get minus 110.5 kilojoules. All right, so let's look at our second equation, double I. Here we have 2 hydrogen molecules. Now, we want hydrogen, but we only want one of them, and we want it to be as part of the products, not part of the reactants. So we're going to divide by 2 this one as well. But in order to sort of switch our reactants and products, we're going to multiply by -1. Because right now we have the energy term in with the product, so it's exothermic. But if it was with the reactants, it wouldn't be negative, it would be positive, making it endothermic. So let's also have this by -1. So when we do that, we're going to switch it. So we're going to get our water term divided by 2. It's going to be in the reactants, so H2O, which is actually what we want here. And that is going to give us, so we have an H2, because we're still dividing by 2, and half an oxygen. And the enthalpy change for that, we divided by 2, essentially divided by -2, we got positive 241.8 kilojoules. All right, so now that is done, look what happens when we add these two equations together. First of all, we have a half oxygen on both sides, so they are going to cancel. And then we're going to end up with, we've got a water here, and we've got a carbon here, and that's going to give us carbon monoxide plus an H2. Right there, that was our target reaction. So now all we have to do to figure out that enthalpy change for the reaction, we are going to add these ones as well. So when we add 241 plus -110, we get positive 131.3 kilojoules. So it's positive. We know it's endothermic. So technically, if we wanted to write that into the reaction, it would be with our reactants right there. All right, for this question, we have to use the standard enthalpies of formation, which I've included over here in this table. to determine the enthalpy change for this reaction. So what we have to do to figure out the enthalpy change for this reaction, we need to take the sum of all the enthalpies of formation for the products and then subtract the sum of all the enthalpies of formation for the reactants. Right, so for this one, let's start with our products. So here are our products. So first we have 3 moles of carbon dioxide. Now carbon dioxide, the enthalpy of formation is minus 394. So minus 394 kilojoules per mole. So kilojoules per mole. The moles will cancel because we're multiplying by 3 moles. Actually, let me write that in so we can see them cancel there. There, moles cancel. Okay, and then it's a sum. So we need to add for water, so 4 moles, times the enthalpy of formation for water, which is minus 286. So minus 286 kilojoules per mole. You can see our moles cancel. Now we need to subtract all of them for our reactants. Now, for oxygen, the enthalpy of formation for any element is going to be 0. So we don't need to consider that one. We just need to consider our C3H8, which is minus 104. And we only have 1 mole of that. So 1 mole times by negative 104 kilojoules per mole. So when we plug all of that into our calculator, we get negative 2,222 kilojoules for this reaction. All right, so next on our list, we are going to be completing nuclear reactions or nuclear equations. So the first one, we have uranium-238. So this number is our total number of nucleons, or the number of protons and neutrons. And this number is essentially our charge, or our atomic number, which tells us just the number of protons. Okay, but when we have an electron, as you can see right here, electron doesn't have any protons, but we write -1 because it tells us the charge. So what we have to do is to make sure all the top numbers add up. That's essentially a conservation of nucleons. And we have to make sure all the bottom numbers add up because that's essentially conservation of charge. So if we look at the first one, we start with 238, and that gives us 234 plus what number do we have to put in here? So 234 plus what will give us 238? The answer is 4. And in the bottom, we have 92, and 92 gives us 90 plus what? So it's got to be a 2. And then you can look on your periodic table to see, okay, which element has an atomic number of 2, and the answer is helium. So this is what we consider to be an alpha particle. So this reaction is an alpha decay. Now our next one, let's do the same process. So we have 214 is equal to 214 plus, well, that's got to be 0. And over here we have 83 must be equal to 84 plus, oh, that's going to have to be a -1, right? Because 84 subtract 1 is 83. So what is this? This is our beta particle, a high energy electron. So this is a beta decay reaction. Looks like the next one is as well. So if we have a -1 here and an 82 here, this is going to have to be 83. And 210 plus is equal to 210 plus 0. Right? So looking on our periodic table, 83 is bismuth. Finally, this last one, this looks like it's also a beta decay. So we have 137 up here And 56 minus 1 is 55. So which element is 55? It's easy. All right, for our last question, we are going to determine the energy that is theoretically released for 1 mole of lithium produced from hydrogen and neutron. So let's write our equation. So we are producing lithium. So that's 7 and 3. So how many protons do we need? We need 3 protons. So that's with 3 hydrogens. So we're going to need 3 moles of this hydrogen. And then in addition to that, how many neutrons do we need? So remember, this 7 is the number of protons and neutrons. So it's 3 protons and 4 neutrons. Okay. So what we need to do now is determine, okay, well, what's the mass of all our reactants and what's the mass of the products? So for the products, we already know. So it is 7.0160 grams. Okay, because the mass of 1 mole, because we only have 1, is this much. And now, what about for our reactants? So let's see, we have 3 moles. So the mass of all of our reactants, we have 3 moles of hydrogen, which is 1.0078 grams for every 1 mole. And then we have 4 moles of neutrons, where 1 mole of neutrons is 1.0087 grams per mole. So that's going to give us a total mass of 7.0582 grams. So that's what we got here, 7.0582 grams. And then notice that mass is not being conserved. We went from about 7.05 to 7.01, so mass was lost. So because mass was lost, energy was released equivalent to E equals mc squared. So we can determine that energy by putting in the amount of mass. And the amount of mass we have to put into this equation is going to be in kilograms. And so we need to figure that out. So our mass that was lost, so delta M, mass lost, is going to be, let's find the difference between these. So we'll do absolute value because we don't care about a negative. So 7.0582 grams minus 7.0160 grams is about 0.0422 grams. And to figure out kilograms, divide that by 1,000. And we have 4.22 times 10 to the minus 5 kilograms. So we can take that mass, 4.22 times 10 to the minus 5 kilograms, multiply it by the speed of light, which is 3.00 times 10 to the 8 meters per second, and square it. We get a total energy of 3.798 times 10 to the 12 joules. Or if you prefer kilojoules, 3.798. Just divide by 1,000 or subtract 3 from our exponent here. There we go. I hope that tutorial helped. If you have any questions, let me know in the comments. And don't forget to subscribe and check out all the types of videos I have in my playlists.